Here we go into one of the most classic of classic problems, whatever that means, with related rates. It's the cone problem. It's one that strikes fear in the hearts of pretty much every single calculus student at first. I'm going to go through it logically though, and I hope to break it down so that you're not fearful of it anymore. Let's do this! A cone-shaped tank with vertex down is 10 feet across the top and 12 feet deep. So I think this is actually a good one to draw out. So I guess I'll draw out my cone right here. So vertex down. So we've got, it's 12 feet deep, 10 feet across, so something like that. It's not a perfect drawing, but that'll do, right? So you got your cone, vertex down. And here's the thing, I am going to draw in the fact that it's 10 feet across, which would give it a radius of 5. The reason why I can draw that in there is that these values are constant. The tank is not going to change in size, right? And so then you've got this amount right here, which it says it's 12 feet deep. That's constant. So any constants I put in pictures. If a liquid is filling the tank at a rate of 10 feet cubed per minute, okay, so now we've got cubic feet, which right away tells us that we're talking about volume. So I'm going to immediately call up my volume formula for a cone, which is pi over 3, or 1/3 pi, r squared h. Now, if you don't know that formula, your teacher wants you to memorize it, fine. On the A, B, or BC exams, they won't ask you to memorize it. They'll provide it for you. Okay, now, normally I'd say take a derivative at this point, but remember you should always look on both sides of the equation and ask yourself, will taking the derivative of time be difficult here? Well, dv dt is fine, but on the right side of the equation, though this is a constant coefficient, it will be pi over 3, it's just along for the ride, we would need the product rule. And so that would be r squared times dh dt plus h times the derivative of this, which is going to have an r and a dr dt. Oh, that's a dh dt, an h, an r, and a dr dt. You're introducing 2 new variables and keeping the other 2 variables. That's way too many variables here. So we're going to need to rewrite one of these variables in terms of the other. That's why we do that, to make life a lot easier. So the problem here is actually more difficult to get to the calculus part. The calculus part's easy. It's getting to a point where we can take a nice derivative that's challenging, but that's why we're going to do what we're about to do. If a liquid is filling the tank at a rate of 10 cubic feet per minute, find the rate of change of the depth of the liquid. So it is important to note that we're looking after dH dt. And when the liquid is 8 feet deep, when h is 8. Meaning there's no information here about finding the radius whatsoever, which tells me I should solve for the radius in terms of the height. Get rid of r completely. That's why it makes sense to do that. All right, let's roll. So one thing to draw in the picture is we've got some kind of height going on here. Right, so you've got some height of water or any kind of liquid in here. And what we end up seeing is you actually end up with a triangle, if you think about it this way, inside of a triangle, where you have a height that is unknown. And I guess I'll do that in different colors here. I'll do that in black. So you've got the height is unknown and the radius is unknown. They're changing. So you'd say, well, the height is 8. Yeah, but it's changing. So I put an h down. And the radius is changing because as this circle, imagine this cone is, you're looking down at this cone, this circle is growing. So the height of the amount of liquid, the depth is changing as well as the radius. So we put variables down. So how are we going to solve for r in terms of h? Well, not so bad really. You've got a triangle inside of a triangle. This is h, this is r. Remember this entire length right here, this thing right here is 12. That's unchanging. That's the height of this cone. And then this radius is 5. That's unchanging. So I take the big triangle out, and I consider that. That's 5 to 12. And now the little triangle I take out, and that's r and h. So we're going to set up a proportion here because they're similar triangles. So I'll do r over 5. Corresponding parts, r to 5 is h to 12. And there's other ways of doing this. Some people will do 5 to 12 equals r to h. That's perfectly fine. Remember, I'm solving for r because it's r that we're not asked about at all. It's h that we want to know about. So by solving for r, we keep everything in terms of h. I multiply both sides by 5, essentially multiplying by 5 and by 5, and that gives me 5/12 h. That's huge, dudes. Super huge, because now you got 5/12 h. That is r. So I'm going to take that and plug it in for r. All this setup just to be able to take a derivative. So pi over 3 times r squared. So that'd be 5/12 h. The numbers will get gross, but we can handle this. Squared times h. Oh yeah, we're getting there. So again, now we got one variable on the right side, and it's the variable that the problem is in terms of. If the problem gave you information on the radius and asked about the radius, we would have solved for h in terms of r. So we've got pi over 3. I'm going to write this with some nice numbers here. That's 5 squared is 25. Over 12 squared is 144. H squared times h is h cubed. Again, I have yet to take a derivative. This is all set up. So the volume is equal to, let's do this out, 25 pi over 3 times 144, which whatever, I'll just leave it as 3 times 144 because watch what's going to happen. Now, we're going to eventually take a derivative, right? So we're ready. Now I know it's safe to take a derivative because taking a derivative of h is fine. Taking a derivative of v is fine, and that's just a coefficient. So we take a derivative with respect to time, I'll do that in a slightly different color, is dv, slightly different, blue. dv dt is equal to, this is all one big coefficient. It's gross, but we're leaving it. You'll see why I didn't multiply by 3 in a second. Times, the derivative of h cubed with respect to t is 3 times h squared, chain rule, da-ha-da-da, or dh dt. That's the chain rule part there, h derivative with respect to time. Now, see the 3's? They're gone. I knew that was going to happen, so I left it out. And so now we're left with dv dt is equal to 25 pi all over 144 h squared dh dt. It's clean. So all of this work was done so that you could get a derivative that was easy to take. And it seems like a long time to do this, but when you get better at this, it's much quicker. All right, so now from here, I'm going to take my values and plug them in. Now we're given dv dt is 10, and it's filling the tank. So dv dt is equal to 10 cubic centimeters per minute. We're already told when the height is 8 feet. Not cubic centimeters, just kidding, cubic feet. How dare I mix up those units? So tragic. So now we're just going to take our numbers, plug them in, and solve. So I've got 10 is equal to 25 pi over 144 h squared. That's 8. So that's times 8 squared, which is 64, dh dt. All that's left for us to do is to solve out. And I'm going to leave this unsimplified. You might be like, you're going to do what? Your final answer is going to be, and this is going to be gross looking, 10 over all of this. This is one big number, right? Get used to just thinking about it that way. It's one big number that's being multiplied by the variable we want to get alone. So think of this as number times variable. We divide both sides by that number. There's that number. And that would be in feet per minute because it's change in feet over change in time, which is minutes. And that's duh-duh-duh. And that is one of the more difficult related rates problems. The most important part here is that you review why it is that we're going through this heavy process to get 5/12 h. When you get that and understand that we're just trying to manipulate this so that the derivative is easier, you'll see that the calculus is actually not so bad. And then we're just plugging in numbers. It's the geometry that's the gross part. And by gross, I mean beautiful.